Hello everybody. Um, Welcome to this live stream. It's my third live stream on YouTube, so I'm sure it will not be perfect, but I hope that you will enjoy it and that you will learn something. My name is Thomas Neumann. I'm the developer of the SATlive software and of the level check software, but the topic today relates to SATlive. We have the subject of phase. It's based on mainly on the reports in the questionnaire that we put in the web short time ago, basically for the bachelor thesis of my wife. But we got a lot of replies there which are interesting for me and for the software too. So the theme today is phase. Phase is one of the most mysterious things in audio. So we said we don't get any audio, so it would be nice if somebody could post in the comments if you can hear me. Okay, so let's go on here. The main, uh, yeah, since we are able to learn, we've been taught 1 plus 1 yields 2. And this is the thing we know, the things we realize every day in everyday life. But with audio, that's not always true. So this is, I think, one of the problems in understanding things like phase and interaction. So I hope I can clarify it a little bit today. Okay, so um, yeah, okay, thanks for the feedback. I'm glad you can hear me. So it's just a confusing message here from YouTube. Okay, so I've got here one battery, and if we use this one battery for maybe a lamp, you know, it's just a low light. If we add a second one, we'll get much more power. It will be much brighter. I don't know if everybody outside has still tried it. If we need a special position to fit in these batteries, so if we reverse one battery towards the other one, we do not get a lot of power as a result, and maybe depending on the design of our device, we also might get a lot of heat out of this. So don't try this really, except you want to have a YouTube video with exploding batteries or something like that. So as most things in sound, if it comes to scientific look on it, the phase thing is also based on sine waves. So we start with looking on sine waves, or on a sine wave here. I have a nice picture, which is from Wikipedia. And we see two traces here. One is sinus, or sine wave, and the other is the cosine wave. And what we see here is we have a wave which repeats, and we have strange labels on the x-axis, which are not some common numbers. It's, in this case, it's 0, it's pi by 2, pi, and so on. So why this is so? As you might know, the sine wave is based on rotating on a circle. And if we have a circle with a diameter of 2 or a radius of 1, we just have a description of the angle, and the angle can be normally written from 0 to twice pi. And this is how it's scaled. So one cycle is just one movement around a cycle. And here comes the next one. So you see it's repeating, which does not make things easier. And the scale here is related to the period of this wave. So we cannot read an absolute time from this graph. We just know, okay, it goes 2 times full cycle and a little bit more here is what we see, but we don't know, will it take 1 second for a cycle, or will it take 1 millisecond, or whatever. So this is one thing that makes the phasing even more difficult. In phase, we do not have absolute values. We have always things related to frequency, or depending from frequency. And as you see here, we have something that repeats. So we cannot go the way back. So we exactly know for, let's say, pi by 2, we have this value, which is 1 for the sine wave. And this is a single assignment, and it's really deterministic. But the other way around, we do not really know if we have a value of 1, is the cycle pi by 2, or we can change the angle from 0 to 330 degrees, which is absolutely the same, or we can scale from minus 180 to plus 180. Always one full circle in mind, which is 360 degrees, or 2 pi. But if we have a value, if we read a value from 1, we do not know is it pi by 2, or is it something like here minus 3 pi by 2, or so we can't go back to an absolute angle value with a value readout from the trace itself. So if we take a closer look to this thing, we go to SATlive now. I just start some sine waves. I hope. Oh, what's going on here? We can't see any sine wave. I forgot to start my tool. Pardon. Yeah, preparation is the key. Yeah, I know. Okay, so here we go. Now we see here we have oscilloscope view in SATlive, and we see one sine wave, but it's in fact it's two sine waves, but they are exactly the same at the moment. If we shift one, you see it just moves related to the other one. And now we have a difference between those two phases. Two traces, which we can either measure for this, if we know the frequency, which is 1k in this case. We could assign a time, so we have here 0.5 milliseconds, or we can say, okay, it's shifted just half a cycle, which would mean 160 degree, or it would mean pi. which is, as I mentioned before, absolutely the same. So something to note for you is just that phase is in the measurement in audio industry, phase is nearly always relative. That means we need to have two signals that we compare and which will have a difference in phase between them, and this difference in phase is the thing that creates problems or contains the main information. The absolute phase value depends on our reference delay and other settings, so it's not really absolute value, even if we just measure one trace. So, and now we can shift this trace even more. And if we shift it even more, you see if I shift it for 1 millisecond, which is just one full cycle, you can distinguish the both traces again. So this is one of the problems. Now we do not see so both traces absolutely similar, or are they shifted by a multiple of 360 degrees, or if we go to time for our trace, is it shifted by 0 seconds, shifted by 1 millisecond, 2 milliseconds. This will always result in absolute the same picture. So why are we interested in knowing the phase or the difference in phase between the two traces? That's because something happened here which called is interference, and I prefer to say interaction because for me interference sounds always bad. And interaction just means that both traces interact and will affect the result. So to show it to you, I just add both traces here, which I can do in this display. Now you see a third trace, which indicates the addition of both traces, and in this case where we have no shift between the two sine waves or a shift which is a multiple of 360 degrees, we see we have perfect additions. But if we move the trace, we add a little delay to one of the two traces, so you see it's not adding to the full amount, but it's still adding, and it's still a sine wave, so it's not changing its basic behavior or its characteristics as a sine wave. It still is a sine wave, the result, what you hear or what we see, but its amplitude varies depending on the delay. So there are some important points. This where our resulting trace has the same amplitude as a single trace, which is 120 degrees of phase shift. And if I continue to shift further or wrong direction, so now we are 120, and now we are 180. So you see this traces are perfectly mirrored on the x-axis, so the addition will result in a flat trace, which is in this case just an ideal example. And if I go further, move further, you see still addition occurs, and if we have a full cycle 360, we have full addition again. So if we want, and the problem is in real life we could not see a blue trace and a green trace, all we see is the result of the interaction, which is the reddish trace. And now our Yeah, now it's up to us to read the red trace and to get some informations about the relation or about a problem which might be there. And looking on phase or on the relationship in time between the two signals is not so easy because of this cyclic nature. So we don't know if we just see the red trace, we don't know are they perfectly aligned, arriving at the absolutely same time, or are they shifted or with a delay, which is a multiple of the time. So looking at a certain frequency and the phase on at one frequency point will not yield many information to us. So I show you now I have no time shift, no delay, and if I change the frequency of my sine wave to 400 hertz, you see we still have this perfect addition. But if I add 1 millisecond of delay, which would give us again the exactly same picture here with a 1K trace, you see with a 400 hertz trace, it's just a totally different picture. And this makes it again tricky. So if it comes to phase and you're trying to make decisions or read values from phase values, never rely on one point in frequency. Always look on a range of frequency, because this will indicate you what's going on very much better. So I show you on by using just to white noise signals, pink noise signals here, and I just go to MIT module transfer function. And in here you see now we have no phase shift. We have our measurement delay is perfectly right. And now we just measure one input signal. I add second input signal, the second source, and the second source is absolutely aligned in time, which means there's zero phase difference between both. And you see they adding perfectly all over the frequency range, and you get plus 6 dB by adding a second source with the same level. But as soon as I add a delay, I just remove one of the traces and add a short delay to the trace. You see the amplitude, which is the upper window, is still perfectly flat, because just adding a delay wouldn't change any energy content of our signal. You see the lower trace, which indicates the phase, is bending down towards the right, which means that we have the signal is arriving later, or too late, related to our delay set for measurement. So if now we add both traces, you see we have interaction here, which comes to cancellation. And to make it easier to see, I just add a lot more of delay. I just add, as we had before, 0.5 milliseconds. In this case, you see we have 1K. 1K would mean one cycle in 1 millisecond. And our delay of 0.5 milliseconds is exactly half of a cycle, which means we have 180-degree shift difference in phase. And now we have here, after one cycle, which is gives us 2K, we have full addition, and after 1.5 cycle we have cancellation, and so on. So if we have a signal or two signals or the same signal coming from using two ways and adding together, and we have a time difference between both and the point of arrival, we're gonna get this kind of picture, which is called a comb filter. Currently we're using really the absolute same signal with the same amplitude, so we get this one perfect or ideal, let's say. So it's just as it should look right out from the book. So in real life you'll never see it in this deeps, but it will be there in real life, and it's always and everywhere this kind of comb filtering. Now just let's see what happens if we reduce the level of one of the two traces. So I just reduce the level of this trace. Oh, reduce the level, not the delay. Okay, so we go down just by 4 dB, and if we try to read out, we have something here between -8 to +4, which means we have a swing from ±6 dB when we have a level difference in the signal of 4 dB. And now I just go further down. Next point to remember is -10 dB or 10 dB difference in level between the traces, and we still have a clearly visible interaction, which is approximately ±3 dB with 10 dB difference in level. So I just reset my delays to make it now just. And one thing that's often misunderstood with phase is something we in German we say turn, Phasendreher, which means turn the phase, and in English you talk about flip the phase or something like that, and this is wrong because we can't flip the phase trace, but we can flip polarity, which is a different thing. And flipping the polarity will just add 180 degree to all phase values. So if I flip the phase here, we're gonna see our amplitude spectra is still perfect flat because we do not change anything, but our phase now looks very strange here, but it just looks very strange because it's shifted by 180 degrees. And as I mentioned before, the phase is cyclic, and in most displays you have a range from -180 to +180, and if we add 180 to 0, we just have 180, and we are on the range where the phase display wraps around. So we can move the phase display just a little bit. Now we've changed start and end point. We still got 360 degrees difference. Now you see we are perfectly on -180 here. And yeah, it's just reversed polarity. Reversing polarity can be done. Yes, we can do it because we want it to adapt some things, to change the trace, but in mostly it just happens because somebody did a wrong soldering, mixing up pin 2 and 3 on the XLR connectors, or you accidentally press the phase reversal or the polarity reversal button in your mixing console or your software or your controller. And of course, if we have flipped phase, just we now both traces here. If I flip the phase, no, I do not flip the phase. Yeah, it's got me here now. If you flip the polarity or invert the polarity of one of the two signals, you see we gonna reach perfect cancellation here. But if we flip polarity on both traces, we still have perfect addition again, because both are now again aligned. So having the polarity flipped or inverted is not bad by default, but you need to have the same polarity all over your system. So if you have flipped polarity on the two speakers that will interact, you will not create a problem. If one of them, the two speakers, is flipped, you will have a massive problem with cancellation and other artifacts. So now the question is, the goal is to reach a minimum difference in phase when we have two signals that will add. There are lots of situations where we have signals that will add, which might be we have different speakers covering different areas, and there's an area of overlap, or we have one mid-high unit or more of them flying and subwoofers sitting on the ground, and even these two systems have a common range of frequencies where they working. So the one important question is, what tools do we have to change a phase? Well, we've seen some of them. The first one is delay. So if we add delay, the phase will bend down towards the right. As higher the delay, as more it will bend down. So that's the most common tool that we use if we want to match phases. And if we are if we adjust the delay line, we also try to match the arrival time, and which is similar with adding delay and to trying to match. The next tool we can use is to invert the polarity, which will add 180 degrees to the phase, independent of the current frequency. And I just want to show you that every filter, or nearly, let's take it that way, nearly any filter we gonna add to a trace will affect also the phase trace. So when this example you see just a low cut filter, small one, but you see this is what we want to gain. We want to apply a low cut, but you see we are also getting some artifacts on our phase trace. So, and the artifact will getting worse, or more stronger if we use a filter with a higher slope. Now we have 24 dBs per octave on 60 Hertz, and you see it affects the phase very, very strongly. So just we need to keep this in mind, that any change in our crossover filters or other filters will affect the phase trace also. If I just for add, we have both two traces with the same level and the same delay. We do not have any delay on one of the traces, but we have a low cut one of the trace, and we have the other trace is just flat, and we see we have here some cancellations very much above our intended crossover frequency, which is 60 Hertz. So using filters normally, except of finite impulse response filters, which I can tailor to have no effect on the phase or on the group delay, we will have an influence on the phase, even if we just want to work with the phase, with the amplitude. We just want to change the amplitude response using filters. And so now I just removed any filter, and you see we still have perfect addition again. So, and a third possibility or fourth possibility is a wanted modification, which we can do using filters called all-pass filters, which just affect the phase trace and do not affect the amplitude trace. This is a example of a all-pass filter applied. It's a second order all-pass filter where we can change the gain setting, and you see depending on our gain setting the whole thing moves a little bit and well, getting steeper across the region we are working on. So now we have our toolbox with our knowledge, which things we can use to modify a phase, and now we just want to apply our knowledge to an example, and we do a classic thing, which is time alignment with using a high frequency speaker and subwoofer. So I just take a look on my high mid frequency speaker, which in this case is a full version speaker, a full frequency speaker, which goes down to 70 Hertz here, and we're just measuring, and now I want a little bit more power in the low end, so I add a subwoofer to it, and you can clearly see that here something's happening here which is not very Nice. I just make a copy of this trace so that we have something we can compare afterwards. I call it full stored. Okay. And yes, you see something's going on here. It's not really perfectly fitting. So what we want to do is to take a look on the phase trace. So I just mute my subwoofer again, restart my measurement, and hide this trace. Or I just show it. You see that we have a dip here, over here. We will have less energy here with the subwoofer running, and that's not definitely not our aim, not what we want to gain. So what we do is we just store our mid-high trace. Just call it high. And afterwards we switch to the subwoofer. And very important is now, because the phase, as I mentioned before, is relative. Our phase measurement is also relative. And if we would change the delay used for measurement, maybe to get a better result, or because we're just used to click on the auto set delay, we would spoil the phase relations, because the phase will change them. Now if we take here, we have the red trace, which I think you can see it very fine. The red trace, which indicates our high mid unit, and the light blue trace, which is the current measurement of our subwoofer. And in this situation we see we have the stronger slope, steeper slope here for our mid-high unit, and the subwoofer is nearly flat. It's also going up here, so we can adjust our phase, because we can bend it down by applying a delay, but we could not bend it up, because we would need negative delay to do so. So in a case, if we would need negative delay, we would have to change to the other speaker and add delay to the other speaker, to our reference. So I just add some delay to our subwoofer. And I want to add it to the subwoofer, not to our. So as you see, while I'm adding delay, the phase trace is bending down. I just zoom a little bit in here to the low frequency area, so you can have a better look on it. You see, we have very close now, below 50 hertz, but there's still some way to go, because we are interested in the area where both amplitudes are similar, which is around our crossover point. If we have a very large difference in level, the phase relationship does not matter much, because the levels are too low to interact. So let's see, we have now and looking on the area of interest around our crossover frequency, we just add some more delay. Just go now. We have exactly 10 milliseconds here. And you see we are really close. We just can add a little bit more, but it will not. Just do it's not too much here. Go back. So yeah, you see what we're doing is to match the phase response, because we know if we have a little, not if we have no or just a little difference in phase, then we will have addition, and this is what we want to gain. So I just turned it in by hand now, and now I activate our mid-high speaker again, and we see what's happening. We see we have some addition here, and we can compare it to our start frequency response, which is light brown or color here. And you see we've gained a lot. We've gained some energy in this area, and we removed this dip, this cut here in the frequency response. And yeah, we did it. We have a really fine result. Achieved a really fine result here with just adding a delay. Now we have added a delay with approximately 10 milliseconds, which is a high value, which is approximately 3.3 meters. And now we just try another way. Just store it here for reference. I just call it just delay, and reset the delay, and again just remove this one or two traces and go back to this. And now we just try another approach, which is we just started with inverted polarity, and now we see we have better fit here in the area where we have the dip before, but we still have here areas with large difference in phase. So even in this case we would need to add delay, and see if we get a better delay value here, but I think we will not, but let's try here. So if we adding delay, you see the trace is coming down again, and we see with the slopes are getting more and more parallel in the area of interest, but they're not overlapping. So we might go for parallel traces here, something like that. But you see, if we're getting our traces, the slope of the traces to match, here we are very similar, here we are similar, but we have a strong difference, and this difference is about approximately 180. So the approach using the inverted polarity will not bring us better results. It would lead to even higher delay values if you try to match the phase traces. So I just keep on adding delay. Now we have 15 milliseconds added. Now you see the traces are coming close on some situation, some points, but we're going to be different on others. So yeah, you see we have fit in this area, but we can live with here. But here we have lots of jumps again, and we have about 16 milliseconds. So it's too high value. So I suggest we just stay with the one we found before. I just want to show you that there are different possibilities. We now could also try filtering to add filters, but the basic principle is always the same. We're trying to match the phase traces. We do not head for a flat phase trace of a single speaker, which can easily be done using the measurement delay, but we try always to minimize the difference in phase, because the difference in phase will create problems. We'll not need to match them perfectly all over all frequencies, because there is a wide range of difference in phase values that will bring us still addition. I just show you a picture that hopefully would clarify this a little bit to you. This is a so-called phase cycle. I think you've seen it. It's just a picture related to this stream. And on the top you see plus 6 dB and 0 or 360 degrees. And even with 90 degrees difference in phase, we still have 3 dB addition. And if the difference in phase grows up to 120 degrees, we just do not have the result will not degrade, it will just not get better. So it's important to try to be in the upper half of the cycle, which means the difference in phase should not be larger or above 90 degrees. If you want to match it perfectly, you can even head for smaller differences, but it's really difficult to achieve over a wider range of frequency. On the opposite side, you find 180 degrees and perfect cancellation if the levels are similar. So you might use this as a target if you're creating directional subwoofer patterns. In this case, you might aim to perfect cancellation in order to reduce the power sent to the back by the speaker. But normally, for the tasks that relate to the visitors, to the audience, you try to achieve a value of phase difference that's a minimum over the area of interest. And the interesting area is always the area where both levels are similar. So it's clear that it does not make much sense to match the phase response of both speakers in this configuration on 1K. So, but we have to match it on the area where they overlap and have a similar amplitude values, which is here a relatively large area. Normally I would cut a little bit the lows from the top and maybe a little bit highs from the upper frequencies from the subwoofer to reduce the width of the area of interaction, because as smaller your area of interaction is, as easier it is to achieve a perfect or nearly perfect phase difference of 0. So that's a little bit theory, and I showed you how to try to match the phase traces, and now I just will show you some two tools we have in SATlive which will help us with this task. First of all, let me just switch back to full display here. One tool is, let's see, yes, let me just reduce all. One tool we have here, and which is very helpful in this situation, is the so-called delay suggestion tool, which just calculates the addition for different delays and looks which addition will give us the best result. So to invoke this, we just go here to Suggest Delay menu and select the second trace. The first trace is always the current measurement, the measurement which is running, or the fixed trace we've loaded into the current measurement. And in this case, we just see it suggests us the high trace. We also have a list of the traces available here. And if we, as soon as we select this trace, we're gonna get a result. Not only one result, we got a lot of results here. We have maximum power, which just is, if we look at the amplitude of the result of the addition, which delay would yield the highest amount here. We have as fast as possible, which does not make much sense here because we have a bus boost and we want to keep that boost of the subwoofer area, and we do not want to cancel reduce it. And the third one is called average of summation, which is very close. Oh yeah, thank you. It happens again. It's the same on the webinars. I just show you a nice picture and then jump back to SATlive and forget to take you with me. So I close it here, and now you will. So we have the delay suggestion tool over here. We have in the menu some trace which is suggested by SATlive, which is normally, if you just show one quick trace in the background, this trace, you can also use the select fixed trace entry here and choose the quick trace you want to use as a second trace. And the first trace is always the current measurement, which is the light blue here. So we use a high one, and after a short period of time, we've got the results here. We have maximum power, which just means would yield the maximum of a result. And we have a thing I want to explain, which is called average of summation. Average of summation does not take the overall energy in account, because if you only look on the energy, which we do on the maximum power approach, we will focus on areas where we have a lot of energy available from one speaker, from a single speaker, and maybe we do not want an optimization which is which boosts the best frequencies, but we want to have a summation where we have the average of the phase of the difference in phase values of the traces is as less as possible, so that always other frequencies, other frequencies are also taken into account. And you see here a line on the bottom of the amplitude area, which is red and green. What is it? What is it, and what does it indicate? By the way, we've got 10 milliseconds by as we try to optimize by hand here. So we have a setting in this menu which is called Amplitude Difference Threshold. As I mentioned before, the effect of this interaction is as larger as lower the difference in amplitude is between the two traces. So I can tell the tool just focus on areas where the difference in amplitude is just below 20 dBs, which yields just this area. Green indicates the area where it does a calculation, and red says in this area the difference in amplitude level is above this limit, so I do not have to do a calculation here. So it just focuses on this area where we have interests. So I just if we do not use this, if we off it, by default it calculates the whole frequency area, or we have to mark an area of a frequency area that we want that SATlive focuses on. So I just removed this setting and you see it will take a little bit more, and you see this result is nearly the same because it's dominated here. By the average of summation, it's a little bit different because now we have the average value all over, and there's still some information here at higher frequency coming from our measurement, which would not normally make sense, but are also taken into account. So I suggest that you use this feature, especially if you use this tool to align subwoofer to top, let's say with 40 dBs. You see we're covering a larger range here, and we have slightly different results, but basically the results are very similar. So this is a powerful tool which helps us to find delay values, and it might also suggest an inversion if this would make sense. And it will give us a maximum of 4 different values, and the first one is just the optimization with just using the delay. The second one is the optimization which we will be done with the polarity inverted of one of the two speakers, and the lower two are just values with a definitions that the delay value must be not less than 0, which would mean that it must yield a value that will give us that we could reach with delaying our current speaker. If we get a negative value for the best fit, we would have to delay the other speaker, which creates this quick trace. Yes, so this is our tools which will help us to get perfect or nearly perfect matching phase traces. So um, phase is somewhat related to time, and in our business, mostly we are looking on difference in phases. Yeah. So and you can read out phases phase values in SATlive very easy, but as I mentioned, the phase value depends on the reference delay. So just doing here some reading of an absolute phase value will not help you very much. The difference of the phase values between two traces, which need to be created using the same reference delay for the measurement, will be very more interesting because it will show us how both will interact. Yeah, SATlive does also do uh, trying to get unwrapped face value or unwrapped face value if you activate it in the settings, but so that we do know are we in the first cycle or have we something over 360 degrees. So, but by default it shows just plus minus 180. So just try to see if I can. So let's see. I normally don't use it because it may be confusing. Yeah, if you're using, you see in the right area here now, it shows something like minus 729 or something like that, which just is now easy to guess, because you need to make a guess to get it, and normally you start at very low frequencies and say, okay, I assume on very low frequency we are within the first cycle, and each jump will indicate a new cycle. So now we got a value which is see, we have 380 here, 360, sorry, pardon. And if we go above this, it does not wrap around. But this value might be helpful, but in most cases it's just more confusing than it helps. So it's an option. I normally don't use it. So, yeah, it's more than 1 hour. I thank you all for joining. I hope that it will give you some information, maybe that it clarifies some things, that it will be some help for your work. Thank you all for watching, and yeah, have a good day. Oh, bye. Yeah, you just might add some comments, especially if you think it would make sense to have more streams on YouTube like this one, or if you say no, just make some shorter videos like some are here available. Yeah, any feedback is very appreciated, and just let me mention it. If you did not take part in the second survey of my wife, it would be nice if you would do so. You'll find the link on the SATlive website, satlive.audio, or on the Facebook pages.